So let's look at some numerical solutions for this model and see what happens as we vary the parameters. So I've defined the parameters up above. One thing to note here is the way that I've set it up here, BH is actually the death rate rather than the birth rate. It has a negative sign in the equation. And so a positive value here means basically that without food, the hawks would, their population would decrease rather than increasing. So with that in mind, we can go ahead and simulate this. And what you see is very similar to what we showed in the previous example. The hawk population starts very low. The squirrel population shoots up very quickly because the squirrels have as much food as they could want and no predators. But soon the hawk population grows and the predators start taking out the squirrels. And so eventually the squirrels will go extinct. And then after that, the hawk population will diminish as well. And as we change parameters, you'll see that the timeline of this changes. We may even have multiple spikes like this, but in the long run, it appears that we're getting the same sort of behavior. So again, I can change these parameters around, but you keep getting, let me run it a little longer here. You keep getting them both dying out eventually. All right, and the reason for this is the squirrel population is allowed to just grow, grow, grow. There's really no limits on it as we set up the original model. And as we saw a few videos ago in our yeast model, that's really not all that realistic. A better model would account for the fact that the environment can only support so large of a squirrel population. At some point, the squirrel birth rate needs to decrease. And so if we modify our model just a little bit, so instead of having beta s times x for our birth term, we have beta or bs times x times some factor like 1 minus x or 1 minus x over a constant, then what that will do is it will decrease the birth rate once the number of squirrels reaches the capacity of the environment. So I'm going to switch over to another script here, where here, let me just highlight the relevant parts. I've adjusted the birth rate term by this factor that says 1 minus the number of squirrels over the maximum population size is going to adjust the birth rate. So if the number of squirrels is small, that's basically going to be a factor of approximately 1. But if the number of squirrels gets close to P max, which is 10,000 at the moment, then we'll see that the birth rate should drop off. So the squirrels can't just overtake everything. And once you do that, you can get a whole bunch of interesting behaviors. So let me run this. All right, so here's one set of parameters. And here I've got actually just rows of a matrix storing my parameters, and then I'll fill the values in later on. And you see we've got initially the squirrel population spikes, but then it drops again. And this is due to the fact that we're close to the capacity of the environment. So they overshoot, and then some of the squirrels are going to die, and then they go back up. But gradually the hawk population increases, and they start to keep the squirrels under control, and we can actually have oscillation that emerges. If we change the set of parameters just a little bit, you can see other interesting things happening. So here, it's a little more consistent pattern of oscillation. Both the hawks and the squirrels, you can see, seem to be bouncing back and forth over a relatively narrow range. And for a different set of parameters, we can still have the extinction events like we saw before. And you can even have really, really dramatic spikes. Let me go to the last one really quick, which I think is the most interesting. So here we've got this cyclical pattern of behavior where the squirrel population goes up, the hawk population then lags behind a little bit, it goes up, and that causes the squirrel population to drop. And then this repeats a few times. And if we simulate that for a little longer, we'll see that that could repeat multiple cycles and eventually have one of them die out. Or if you tune the parameters just right, you can get that to go on pretty much indefinitely. There we go. So there it looks like we've got a very repetitive pattern that persists forever. So I show you this example to help illustrate the following principle. When you have a high dimensional model with multiple state variables and many parameters, it's very difficult to predict exactly what's going to happen. There's a whole rich set of different behaviors that you can see in a system like this one. And just experimenting with different parameters gives you some sense of the possibilities, but we have not even scratched the surface of all the different things that you can see in this model. And so if you want to fully understand what's going on here, we need a better technique than just plugging in different parameter values and running a simulation. And so in the next set of videos, we're going to look at some analytical techniques, not for describing exactly what the state is going to be at each point in time, but for understanding what the long-term behavior of the system is going to be. All right, so that'll wrap up this unit. We will talk about fixed points and stability in the next batch of videos.